This video is for the MPAS module. It is a residual statics program. As with all surface-consistent static programs, geometry errors can significantly degrade the static solution. MPAS is additionally susceptible to significant R&MO errors. There are a fair number of parameters, only a few are critical. The survey type, the choices are 2D or 3D. MPAS allocates memory differently depending on whether this is a 2D or a 3D survey. The smash bin width and the smash line width determine how many CDPs are averaged together. The program does not account for structure, so having these too large can also degrade the solution. The correlation window can either be single window or multiple windows. If you have a zone of the data where the signal to noise is significantly better than others, use a window that follows that zone. Otherwise, a single window covering the entire trace is usually pretty good. The maximum static should be at least plus or minus a dominant period of the data. Restricting this too much can miss good static values. The number of iterations defaults to 4. MPAS computes a static solution and outputs the shot and geophone correlations every iteration. The statics are applied for the next iteration. The solution is cumulative. If the solution looks reasonable, you can stop MPAS and use the current values. There are a couple of things to look for in the execution status. The average shot and geophone correlation fold tell you how many traces contribute to the average static. This may increase between iterations as correlations typically get better and fewer are thrown out. The maximum statics probably won't change, but the average change in static should decrease between iterations, as it does here. MPAS has two output data sets. These outputs are not required to run MPAS, but really should be output and looked at. They are important QC tools. Both look somewhat similar. What you expect to see is a band of data for each correlation. The traces within each band should look like autocorrelations. If they are notably asymmetric, there is a problem, either geometry, R&MO, or a leg jump. In the first iteration, the traces may look rather jittery, as they do here. This should decrease between iterations. As you see, these get smoother. They also typically get a bit stronger. The trace headers on these outputs are rather restricted. Only MBin, fold, and SSTS and SSTG are valid. MBin contains either SSPN or SGen for the shotter and geophone output. Fold contains a number of traces that contributed to the static, and SSTS and SSTG contain the current solution for the shot or geophone statics. You can observe these. For instance, here is the fold header. The fold should reasonably track the correlation amplitudes. A high fold or low amplitude correlation is a potential problem. Looking at this is what we've got here. These are the statics for this particular data set. There's nothing particularly startling here. If you look up here, things were jogging up here or have negative statics, and vice versa. The shot correlations look very similar. Notice the amplitudes track the fold a bit more obviously in this particular case. And again, the statics on this data set aren't that extreme. Probably the biggest ones are over here. You can see the positive kick here and a negative static, another positive kick here and a negative static, and the rest of them are fairly reasonable looking.